So in this part of our class, we're still going to continue talking about solving trig equations or equations with trig functions involved in them. But this time we're going to be including angles that get a little bit fancier. And so what do I mean by fancy angles? Well, let's look at an example. So we are asked to solve for x on the interval from 0 degrees to 360 degrees. And by the way, notice how the interval is given in terms of degrees. So as soon as I see that my interval is in terms of degrees, that means that my final answer should be in terms of degrees. So anytime you're reading one of these problems, it should either tell you an interval that involves degrees, or it should tell you an interval that involves radians. And whatever that interval is in, that's how you want your answer. So in this case, we want our answer to be in terms of degrees. So final answer in terms of degrees. And again, we are looking for all values of x on the interval from 0 to 360 degrees. So we're going to look one time around the circle. Okay, so we're looking for all solutions between 0 and 360 degrees. Okay, so now we have 2 cosine of x over 2 minus square root of 2 equals 0. And so here I do have an equation that involves a trig function. And what I mean by a fancy angle is the part inside the argument, cosine of stuff. Well, that part inside the parentheses is fancier than just an x, or fancier than just a theta. Okay, so looking at this equation, I see that there's fancy stuff going on inside the parentheses, but I'm going to ignore that part for now. And what I want to ask myself is, what type of equation is this in terms of the trig function? So we have a cosine function here. There's no power on the cosine. So what that tells me is that this equation is linear in terms of our cosine function. So in terms of cosine over 2. So our strategy in beginning this process is to isolate that cosine of x over 2. Okay, so to do that, I can add square root of 2 to both sides. So we would have 2 cosine of x over 2 equals square root of 2. And then I can divide both sides by 2 to cancel the 2 in the front. Notice that this canceling does not affect the stuff inside the parentheses in any way, shape, or form. Okay? So I'm not touching what's inside the parentheses. So what we have now is cosine of x over 2 is equal to root 2 over 2. Okay, so in this example, we isolated cosine of x over 2, and we have root 2 over 2. Up until this point, we've completely ignored the fact that there's fancy stuff inside of the parentheses in the argument or in the angle of our cosine function. I want to pause now and talk about how this fancy angle affects things. So when we have something fancy inside the parentheses like an x over 2, what this does is that this angle affects the interval where we look for angles. So, for example, part of the reason that this happens is when we have something like cosine of x over 2, another way to write that is cosine of 1/2 times x. X divided by 2 is the same as 1/2 times x. And so this number in front, when we talked about graphing functions, this number in front was our b value. And that b value affected how much we either stretched or compressed our functions. It affected the period of the function, how many waves we got between 0 and 2 pi, okay, or how long it takes to get through one complete wave. So in general, what happens is that if we have something fancy inside the parentheses, we want to check for solutions to cosine of b times x or sine of b times x or any of the trig functions, tangent of b times x, whatever the trig function is. I look at that number in the front and we want to check for solutions to the equation involving this trig function b times around the circle. So in our example, we have cosine of 1/2 x. So rather than looking for solutions one complete rotation around the circle, we're only going to look for solutions halfway around the circle. Okay, so we are looking at cosine of x over 2 equals root 2 over 2. And because we have this x over 2 inside the parentheses, we are going to be searching for angles only in the top half of the circle. Because we have the x over 2, that's the same as 1/2 x. So this 1/2 tells us only the first half of our circle in terms of angles. Okay, so that means we can ignore quadrants 3 and quadrant 4 completely, and we're going to be looking for angles where the cosine value is positive. Now, when the cosine value is positive, we're talking about angles in quadrant 1, because cosine is positive in quadrant 1. Cosine is also positive in quadrant 4, but I don't care about quadrant 4 because we only care about angles from 0 to 180 degrees. Okay, so we are looking for an angle in quadrant 1. Cosine is negative in quadrant 2, so we're going to ignore that one. That means that we really only have one angle that we're looking for in this particular example. Okay, so our value is root 2 over 2. And when I see root 2 over 2, I recognize that is the rationalized version of 1 over root 2. And when we're talking about the cosine function, cosine of an angle is opposite over, that's wrong. Cosine of an angle is adjacent over hypotenuse, or x over r. And so what that tells me is that this top value is our x, so our x is equal to 1, and our bottom value is our r, so our r is square root of 2. And so when I look at this triangle and I kind of stare at it, I say, okay, I recognize those numbers. These are numbers that go along with our 1, 1 square root of 2, which is our 45, 45 right triangle. And that tells me that this angle right in here, our reference angle, is 45 degrees. That's also pi over 4, but remember in this problem we are looking at answers in terms of degrees. So I can think strictly in terms of degrees. Our reference angle is 45 degrees. So what this says is that cosine of x over 2 is equal to root 2 over 2 when that thing inside the parentheses is equal to 45 degrees. So that thing inside the parentheses, the x over 2, that angle is 45 degrees. Okay, now if it was just a plain x inside the parentheses, we'd be done. X equals 45 degrees, done. But that's not the case. What we have here is x over 2 equals 45. So I have one more step here, and that is to solve for x. So to solve for x, I can multiply both sides by 2. They cancel on the left. Leaves me with x equals 90 degrees. And so what this tells us is that in our original equation, 2 cosine of x over 2 minus root 2 equals 0. If x equals 90 degrees, then this left-hand side will simplify to give us 0. Okay, so that wraps up that example. We have one example left to look at. In our final example, we would like to find solutions to the equation cotangent of 3x equals square root of 3 on the interval from 0 to 2 pi. Okay, so I see that our interval, we're looking for x values one time around the circle, and I see that the equation that I have, and one time around the circle, and our final answer should be in terms of radians because this 0 and this 2 pi do not have degree marks on them, so they must be radian measurements. Okay, now our equation that we're looking at is cotangent of 3x is equal to square root of 3. And the first thing that I want to say about this equation is that when we have things like cotangent or cosecant or secant, those are all of the reciprocal functions. And in my opinion, I personally prefer to work with sine, cosine, and tangent rather than cosecant, secant, and cotangent. So I'm actually going to replace this cotangent of 3x equals square root of 3 with a tangent function. So remember that cotangent of theta is the same as 1 over tangent of theta. So I can rewrite cotangent of 3x as 1 over tangent of 3x equals square root of 3. And now I can rewrite this whole expression so I get tangent of 3x by itself. So how do I do that? Well, I multiply both sides by tangent of 3x. And so I have 1 equals square root of 3 times tangent of 3x, and then I can divide both sides by square root of 3. And so what I'm left with is 1 over square root of 3 is equal to tangent of 3x. So I've rewritten the problem so we have things in terms of tangent instead of in terms of cotangent. Okay? That is a preference thing. You can certainly deal with cotangent, and I would encourage you to try answering this problem in terms of cotangent, but I'm going to stick with tangent. Okay, so we have tangent of 3x is equal to 1 over root 3. Because there's something fancy inside the parentheses, in particular there's a 3 here, this 3x inside of the parentheses, that 3 tells me to look for solutions 3 times around the circle. Okay, we always look for solutions b times when we have a bx inside of the parentheses. Okay, so we have tangent of 3x is equal to 1 over square root of 3. So tangent, let's see, we have 1 over square root of 3. That value is positive, and I know that tangent is positive in quadrant 1. So tangent is positive in quadrant 1 and in quadrant 3. So we are looking for angles in an angle in quadrant 1 and an angle in quadrant 3. Okay. Now, by the way, just as a thought bubble on this, tangent of an angle is opposite over adjacent, or y over x. And so the way that we get a positive value is when both the x and the y are positive, that's in quadrant 1, or when both x and y are negative, that's in quadrant 3. Okay. Now, why am I bringing that up? Well, in our example, we have 1 over square root of 3, which will be our y over x, or our opposite over adjacent. So when I draw my triangles, our y value is 1 and our x value is square root of 3 for our triangle in the first quadrant. But for our triangle in the third quadrant, the x and the y are both negative, so our x value will be negative square root of 3 and our y value will be negative 1. Those negatives don't show up in this ratio because they've been canceled. Negative 1 over negative root 3. Okay, so I've labeled my sides on this triangle, and looking at this triangle in quadrant 1, I see a side of 1 square root of 3, and so I recognize this triangle as having a hypotenuse of 2, and the side opposite of our reference angle is the smallest side, so this must be a 30-degree angle, or in terms of radians, that's pi over 6. And the same is true for our triangle down here in quadrant 3. Our reference angle is 30 degrees, or pi over 6. Okay, so now we want to think about possible values for the angle inside these parentheses. Okay. So 3x could be equal to, our first angle here is pi over 6, or 3x, the thing inside the parentheses, could be equal to this angle that starts on the positive x-axis and ends down here in quadrant 3. Now, if I want to think carefully about this, then let's see, that is 30 degrees past 180, so this angle right here is 210 degrees. So one way I can think about this is 210 is 7 30-degree marks, so that's 7 times pi over 6. So this red angle here of 210 degrees is 7 pi over 6 radians. Another way to think about that is I can break up my circle into blocks of pi over 6. There will be 6 of them on the top half, plus 1 more gives me 7 pi over 6s. Okay, so those are our two angles that we get from one time around the circle. Pi over 6, 7 pi over 6. Okay, we'll swing back to the beginning. That's one time around the circle. Okay. Now, the second time around the circle, I start by saying, okay, I'm going to swing one full time around the circle plus an additional pi over 6. So the next angle that I'm looking at is an angle that goes all the way around the circle, 2 pi, plus an additional pi over 6. So our third angle is 2 pi plus pi over 6. All right. I can also get another angle by swinging one time around the circle plus an additional 7 pi over 6. So we have 2 pi plus 7 pi over 6. And so now, so that was 2 pi plus 7 pi over 6 brought us down here. Okay, we come back to the beginning. That's twice around the circle. And then we can swing up another pi over 6. So twice around the circle, 1, 2, that's 4 pi, plus an additional pi over 6. So we have 4 pi plus pi over 6. And finally, we have 4 pi plus 7 pi over 6. Okay, so this is a pretty long list. We started out with a 3x inside the parentheses, and that 3x could be equal to any of these 1, 2, 3, 4, 5, 6 different possible solutions. Now, some of these solutions look a little bit ugly, so we want to clean them up. And the way that we can clean these up is that we can come up with common denominators. So this 2 pi plus pi over 6, hi buddy, is common denominator 12 pi over 6 plus pi over 6. That gives us 13 pi over 6. The 2 pi plus 7 pi over 6, common denominator is 12 pi over 6 plus 7 pi over 6. So that gives me 19 pi over 6. This 4 pi plus pi over 6, common denominator gives me 24 pi over 6 plus pi over 6. And so that's 25 pi over 6. And our last one, common denominator, 24 pi over 6 plus 7 pi over 6. 24 and 7 is 31 pi over 6. Okay, so our fancy angle of 3x is equal to any of these 6 possible angles. So let me write that down carefully up here. We have 3x, the fancy angle inside the parentheses, is equal to pi over 6, or 7 pi over 6, or 13 pi over 6, or 19 pi over 6, or 25 pi over 6, or possibly 31 pi over 6. Okay, our goal in this problem is to solve for x. Right now we have our angles that are equal to this fancy 3x. So we have 3x equals all of these things. To get the x by itself, we've got to divide everything by 3. And what that'll give us is pi over 6 divided by 3. Well, thinking about fractions, pi over 6 divided by 3 is the same as pi over 6 times 1/3, which is pi over 18. And in fact, all of these denominators of 6 are going to become denominators of 18 when we divide by 3. So our angle of x is going to be possibly pi over 18, 7 pi over 18 when we divide by 3, 13 pi over 18, 19 pi over 18, 25 pi over 18, or 31 pi over 18. And these are our 6 solutions to our original equation, which was cotangent of 3x is equal to square root of 3. Okay. Now, what you might double check is if you were to check any of these possible answers, every single one falls into the range of 0 to 2 pi for x. So when we were finding angles for the fancy angle of 3x up here, we had to change our interval where we looked. So we had to look 3 times around the circle. And the reason we did that was so that then when we divided all of our angles by 3, that 3 times around the circle got crushed down into 1 time around the circle. Okay, so we've got all these angles. Let's do a sanity check on the graphing calculator. Uh-oh, the computer has died. Okay, so we want to do a sanity check on our 6 solutions, and our equation is cotangent of 3x equals square root of 3. Now, on my graphing calculator, I don't have a cotangent button, so I will need to type this in as 1 over tangent of 3x. So 1 divided by tangent of 3x. And my other function, the right side of the equation, is square root of 3. All right, we're clearing that out. Square root of 3. Okay, so that's what we have. I'm going to double check my mode. Good, we're in terms of radians. And I'm going to make sure that my window goes from 0 to 2 pi, because that is our interval for our x values. Enter. And I have an x scale. It looks like it's already pi over 2, but I'm going to just double check that. Pi over 2. Hit enter. And let's graph this thing and see what happens. Okay. So what I see here is I see cotangent graphs. Branches. Makes sense. The cotangent graph starts high and drops down. Because of that 3 inside the parentheses, it's been squished, so we have more branches between 0 and 2 pi than we normally do. And here's the graph of square root of 3. And what I see here is I have 1, 2, 3, 4, 5, 6 solutions between 0 and 2 pi where cotangent of 3x is equal to square root of 3. And if I pick, just for the sake of an example, if I pick one of those solutions up there, maybe the third one, how about 13 pi over 18? And I hit trace and type in 13 pi divided by 18, and I hit enter, I can see that that's the x value where our cotangent branch crosses square root of 3. Okay, that's all for today. Thanks for listening.